let's talk about rational functions. Rational functions, essentially a ratio is a fraction. Uh, Ratio meaning two numbers divided by one another. So when we talk about rational functions, we're going to be talking about functions that have variables in the form of a fraction. There's going to be variables in the numerator of a fraction and variables in the denominator of a fraction to a point which we cannot simplify the fraction and get rid of the numerator or denominator. So we're going to have we're going to start with a basic application of where rational functions come from. Example here says, suppose we know that the cost of making candy is dependent on the number of pounds of candy X produced. This is given by the equation costs C of X equals 10X plus 500. So if I were to produce X amount of candy, then this formula, this function gives me the cost of producing that many pounds of candy? That many pounds of candy. So if we look at part B here, it says determine the total cost of producing 25 pounds of candy. So that first part there is just C of 25, right? Which we know is just 10 times 25 plus 500, which is 250 plus 500, which is 750. So that tells me it costs $750 to produce 25 pounds of candy. Right, that's how the function works, the C of X function. But then it says, then determine the average cost of producing 25 pounds of candy. Meaning, the second sentence here is asking for a cost per pound. Right, so how much does it cost per pound? But it's not saying how much does it cost to produce 1 pound of candy. It's saying how much does it cost per pound if I'm producing 25 pounds of candy. So in order to do average, in order to calculate average, we're going to do C of X divided by X. So if we're producing 25 pounds of candy, then we'll figure out how much it costs to produce those 25 pounds of candy, and then we'll divide by 25 so that we get a per pound amount, right? So in order to answer the second part of this question, we want to do C of 25 divided by 25 to get a per pound amount. We already calculated C of 25. That was 750. Divided by 25 gives us 30. That means it costs $30 per pound to produce 25 pounds of candy. Right, and this should make sense because if you were given this information here that I gave in the answer, it's $30 per pound to produce 25 pounds of candy, you would find the total cost by just multiplying these two numbers together. Right, so it makes sense to divide by the number of pounds to get your per pound costs. Which means if we're doing an average cost calculation on part C, it says to create a formula for the average cost of producing X pounds of candy. We can generalize what we did in part B and say that AX, or A of X, is going to be C of X divided by X. So no matter how many pounds of candy we produce, we would plug that into C, and then we would divide by that X to get an average amount. or the average cost. So let's actually do that. What is C of x? C of x is 10x plus 500 divided by x. So we have a formula, we have a function for the average now, if we just put it in general terms with the x. So this is an example of a real-world situation where you want to find the average cost of producing X amount of candy, which results in this type of function. And we haven't really talked about how to simplify, how to graph, what the graph would look like. So far we've talked about linear functions and we've talked about quadratics, right? Linear functions are straight lines, y equals mx plus b. We've talked about quadratics, which happen when you have an x squared in your polynomial, right? If it's like y equals ax squared plus bx plus c. We've talked about linear functions having a straight line graph, quadratics having a parabola-shaped graph, and now we're going to talk about these rational functions that have a numerator and a denominator and kind of look at the different characteristics of those and see what the graphs look like, see what characteristics we can deduce from examining the formula of the function. Okay, so in the next page, what are we doing here? Use arrow notation. We've seen the graphs of the basic reciprocal function, 1 over x and 1 over x squared. In the toolkit functions, if you go back to your toolkit functions in section 1.1, you'll see these two represented in that big table of toolkit functions. We know that 1 over x squared does this thing where it's in the first and third quadrant, and then 1 over x squared is in the first and second quadrant, where there are certain lines, like this vertical line and this horizontal line, that it never crosses, right? We call those asymptotes. We're going to actually figure out, we're going to talk about how we can find those asymptotes, and the second one here as the same asymptotes. Actually, it'll never cross either of those dashed lines, the axes, because of the way these are structured. That's what this is all saying. So using arrow notation, we would say that on the left branch of the graph, we're talking about this 1 over x reciprocal function here. On the left branch of the graph, which is this side here, it says that the curve approaches the x-axis, this horizontal line here, as x goes to negative infinity. So this arrow notation is just saying where we are moving along the blue graph, okay, along the blue line. So if it says x arrow negative infinity, that means as x approaches negative infinity, meaning we're moving towards the left on this blue graph. And as I move left on this graph, I see that my y values approach this horizontal line at y equals 0. Right, so that's our arrow notation. We can do the same thing for any of the really asymptotes. We can also talk about vertical asymptotes in that way. So if we consider this vertical asymptote here, as x approaches 0 from one side, we're going up to infinity on the y values, and as we approach 0 from the other side, our y values are approaching negative infinity, because these will never reach the y-axis, meaning this line goes up forever all the way up to essentially infinity, because it never stops growing. So a bit of an extra notation on the arrow notation is that we add the little minus and the plus to signify which side we're approaching a specific number from. So this x arrow c with a negative superscript means as x approaches c from the left. So c minus means from the left. So these x values, for example, if we're approaching this asymptote from the left, that means we're on this side of the graph, we're approaching, getting closer and closer to that value 0. And then the rest of this we kind of have already seen before with with end behavior. When we talk about x going to infinity, that means we're going right forever on the graph. If x is going to negative infinity, we're looking at the left end behavior of the graph. And then these are kind of what the y values are doing, or I guess it could be d as well, what the y values are doing as you approach infinity or negative infinity with the x values. Okay, let's talk about the specific example here and fill in some notation. Returning to the graph of y or f of x equals 1 over x, which is the reciprocal function, the simple reciprocal function. We can use the notation above to describe the behaviors as x approaches 0. So as x approaches 0 from the left and the right, we can describe what's happening to the y values of the blue graph. Right? So as x approaches 0 from the left, meaning x is less than 0, so as my x values approach 0 from the left, what is happening to my f of x values? As x approaches 0 from the left, what's happening to my y values?
They go to negative infinity.
They go to negative infinity. So we'll write negative infinity here. And in like shorthand symbolic notation, this is how we'll write that. X arrow 0 with the superscript of minus. That means as x approaches 0 from the left, f of x is going to approach negative infinity. Right? And then as x approaches 0 from the right, as my x values get smaller and smaller but stay positive, then these points on the graph are going to what y value?
Infinity.
Good. They're not approaching a single number. They're just growing without bound, right? There's nothing that's binding them to stop. So this is infinity. So in shorthand notation, as x approaches 0 from the right, f of x approaches positive infinity. This behavior creates a vertical asymptote. So as we have a specific line that the graph is never going to cross, and so it approaches that and it goes up and down to positive and negative infinity, we call that a vertical asymptote, which is a vertical line that the graph approaches but never crosses. So the characteristics of a vertical asymptote is that as x approaches your vertical asymptote from the left, your y values either go up to infinity or down to negative infinity, and then as you approach from the right, same thing happens. Your y values grow or shrink without bound, right? So if you're talking about the behavior of a graph near an asymptote, your y values are always going to go to either infinity or negative infinity, depending on the function values near that point. What's happening? Oh, I see. We can also talk about long run behavior, which is not talking about behavior near a asymptote. Instead, long run behavior is talking about what happens as x goes to infinity and x goes to negative infinity. This is talking about the left and rightmost extremes of the graph, right? As my x values go left, sorry, the first one is asking about as x approaches infinity, meaning as I go right along this graph, what is happening to my y values along this graph? What are my y values approaching? Any ideas?
0.
0. These y values are getting closer and closer to 0, but they never actually reach. So we say that f of x approaches 0. And then if my x values are going to negative infinity, so if I go left really far on the graph, what are these points approaching What are the y values of those points approaching?
0.
Good. Again, 0 on the other side as well. And we have this same kind of behavior in the y values as our x's go left and right, meaning there's a horizontal asymptote at this y equals 0 that the graph will approach but never cross. So that's behavior near a horizontal asymptote, or long run behavior is explained or is written in this format. That's a horizontal asymptote. This is all looking at a graph. Obviously, we've looked at a graph so far. We're going to talk about how to obtain this kind of information. Where is there a horizontal asymptote? Where is there a vertical asymptote? By looking at the function, not as a graph but as an expression, right? So we're going to be able to look at a rational function and kind of pull this information from not necessarily the graph. I'm going to skip this one. Not necessarily the graph, but the function notation given. So if we have a quotient of two polynomials, meaning we have a polynomial on top and a polynomial on the bottom, there's going to be ways of identifying vertical asymptotes and horizontal asymptotes. So let's talk a little bit about that now. Right. So how do we identify zeros and vertical asymptotes of a rational function? Simply put, zeros are going to be when the numerator is equal to 0. So we take the numerator of the rational function, whatever fraction we have. We take the numerator, which is the top half of your fraction, and we set that equal to 0. Right? Once we solve that rational function and find x's, that would make the numerator 0. Those are zeros of a rational function. On the other hand, if we want to find vertical asymptotes of a function, that happens when the denominator is equal to 0. So we're going to do both. We're going to take the numerator on its own, set it equal to 0, and solve. And that's going to give us the zeros of a function. And then we're going to take the denominator, set it equal to 0, and find our vertical asymptotes from that operation. Do you remember what zeros are? We just like to start talking about zeros. What are zeros of a function? Anyone remember what we mean by zeros of a function?
Are they the x-intercepts?
Perfect. They're the x-intercepts. They're when y is equal to 0. So let's do a little a note on this here. Zeros are y-intercepts, which is also when y equals 0. Right? Zeros refer to where the graph crosses the y-axis. And sometimes there are none, like in the examples that we were just looking at in these graphs. The basic reciprocal function here. This has no zeros, right? If we look at the y-axis, the x-axis, the graph never crosses the x-axis. It has no x-intercepts, meaning it has no zeros, right? Which kind of makes sense because there's an asymptote there that we just decided that we saw that the graph would never cross, right? So how we find these is by setting the numerator equal to 0. And if we do look at the numerator of this rational function, the root numerator is 1, right? And if I set that equal to 0, there's no way 1 is ever going to equal 0, right? So that kind of makes sense that there is no x-intercept. There are no zeros for this type of function. But if I take the denominator and set it equal to 0, then I find vertical asymptotes. So x equals 0 is a vertical asymptote, and that's why we have an asymptote at x equals 0. That's the y-axis. Right, so setting the numerator equal to 0 and denominator equal to 0, We find the zeros of the function and the vertical asymptotes of the function. Not need to do that one. You guys can do that. Okay, let's talk about long run behavior because this one is a little bit tricky. If we have a rational function, remember a rational function looks like this. It is some kind of polynomial divided by another polynomial. Right, I'm going to put this up here so we can look at it. If I have some kind of polynomial divided by another polynomial, we have some conditions here. These 3 bullet points are 3 different things that can happen, 3 different conditions to look out for, and they're going to give us different horizontal asymptote types. So essentially we're comparing the degree of the numerator to the degree of the denominator. So we're comparing degree of the numerator to the degree of the denominator in each of these cases. If you guys remember what degree is the highest exponent, the biggest exponent in the numerator and the biggest exponent in the denominator. So if the biggest exponent in the numerator and the denominator have this relationship where the numerator's degree is smaller, less than the degree of the denominator, then you automatically have a horizontal asymptote at y equals 0, which is in the example that we saw with the 1 over x, that is what's happening because the numerator has a degree of 0 and the denominator has a degree of 1. In an example like this, down here, we have a rational function. What's the degree of this numerator polynomial?
Second degree?
Say it again.
Is it second?
Yeah, 2. How do you know that?
Because of the exponent?
Because of the exponents. We look at we find the biggest exponent on x. That's going to be our degree. So this numerator has degree 2. What about the denominator? What's the degree there? 3, which means the numerator on top is smaller. Sorry, the degree on top is smaller than the degree of the denominator on the bottom, which means we're in this first bullet point situation. So if the top degree is smaller than the bottom degree, then we automatically have a horizontal asymptote at y equals 0. We don't even need to check the rest of them because those are different cases, right? These 3 cases can't happen at the same time because it literally says if the degree of the numerator is less than, if the degree of the numerator is greater than, and if the degree of the numerator is equal to, right? Those are 3 different things that can happen, which result in different end behavior, long run behavior. So if the top degree is smaller than the bottom degree, y equals 0. If it's bigger, if the numerator's degree is bigger than the denominator, we have a slant asymptote, which means we're not going to be worried about finding slant asymptotes in this class, so you don't have to worry about, I don't think we're going to find slant asymptotes. Let me double check real quick. Yeah, I don't think we're ever... Yeah, we're not doing slant asymptotes. Just know that that's what happens, just so we have a comprehensive list of cases here that covers everything that can happen. We say that there is a slant asymptote, but we are not concerned with finding that slant asymptote. And then finally, if the degree of the numerator and the degree of the denominator are the same, so if we have like a quadratic on top and then a quadratic on the bottom somehow, then the horizontal asymptote is the ratio of the leading coefficients. Meaning, we take the leading coefficients. So let me find an example of that here. Actually, I don't want to find an example of that there. Let me write a new example here. We have R, H, and G. I'll say f of x. We'll do a little example on the side here. F of x equals 3x squared plus 2x plus 1 divided by 2x plus x squared minus 3. So if we have this example here, the horizontal asymptote question can be answered by looking at the degrees of the numerator and denominator. What is the degree of the numerator?
Two.
2. Good. What's the degree of the denominator?
2 as well.
2 as well, because it's out of order, right? These two are switched. We just look for the highest exponent to find the degree. So degree 2. We can actually write that here. Degree 2. Degree 2. So we see that they're the same, right? They're equal to each other. So we're in this third bullet point case here. So if the degrees are equal, then the horizontal asymptote is going to be the ratio of the leading coefficients. So we need to find the leading coefficients of each polynomial. The leading coefficient, remember, is the number factor in front of the leading term, which is the term with the highest degree. So in the numerator here, that's the leading term. And in the denominator, this is the leading term. I know the denominator is out of order, but if we were to put it in the correct order, that positive x squared would be the first term, right? Because we want to put it in the decreasing exponent order. So that x squared is the leading term, which means if I want to find the horizontal asymptote, y equals, I'm going to do a ratio of their coefficients. The coefficient of the top leading term is 3, and the coefficient of the bottom leading term is 1. So we get y equals 3 for the horizontal asymptote in that situation, because we have this 3 over 1. Right? We just divide their coefficients, and that's where the horizontal asymptote is. Any questions on the 3 cases here, or this example? Okay, so in these examples here, you'll be finding zeros. Do we all remember how to find zeros? You set the numerator equal to 0. We're going to find vertical asymptotes. We're going to set the denominator equal to 0 to find those ones. And then for long run behavior, we need to find the horizontal asymptote so that we can say what happens in the long run, right? So the horizontal asymptote determines long run behavior. And I don't mind helping with these problems, or actually I don't mind helping with anything, but especially on these problems, make sure you ask me to check your answers when you do 1 or 2 of these, because there are specific ways we're supposed to write zeros and vertical asymptotes and long run behavior, right? So for, let me give you I guess kind of a way to write those answers. So if you're doing zeros, you're going to write them as coordinate points, because remember they're y-intercepts. Sorry, they're x-intercepts, right? So we're going to write them as x 1 comma 0, x2 comma 0, and so on. We're going to write them as coordinate points. You're going to set the numerator equal to 0, and then you're going to solve for x's, and however many you get, that's how many zeros you'll have to list, right? But we're going to list zeros as coordinate points, as x-intercepts. When we're listing vertical asymptotes, on the other hand, we're going to list those as x equals, I don't know how to, x equals, we'll say x1, x equals x2, and so on. So when we're listing vertical asymptotes, we're going to list those as equations of vertical lines, right? A vertical line has an equation of x equals a number, x equals a number. So when you set the denominator equal to 0 and you solve, you may get 2 or 3 or 4 different vertical asymptotes, you're going to list those as equations like this, where x is equal to a number, x is equal to a number, and so on. As for the long run behavior, we're going to write the long run behavior as follows. We're going to say as we're going to say as x goes to infinity, your function, whatever it is, I'm not going to write something specific, but it could be r of x, h of x, g of x. I'm just going to put y here. Y goes to something. That's what you're trying to find there. And then as x goes to negative infinity, y will go to something as well. Right, so long run behavior is what's happening to the y values as x goes to infinity and negative infinity. Okay, so this is kind of how you should be structuring your answers here. For zeros, you list points. For vertical asymptotes, you list vertical lines. For long run behavior, you talk about what happens to y as x approaches infinity and negative infinity. Okay, and then we'll stop there because that's where the videos went up to. We'll talk about how to actually graph these on Friday. So you have some